So let's graph with the transformation rules. We identified the transformation rules last week, and now we're going to put it together with the graph. Our goal is to not use a graphing calculator, although I think if you have one, you should check your work with a graphing calculator. And as we look at our first function, h of x equals negative the quantity of x plus 5 squared minus 2, we're going to have to identify the transformations to help us graph. And before we do that, we're going to start by graphing our parent function, which is y equals x squared. We focused on the points last week, and they are 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, negative 4. And the board is disoriented over here to the left, so sorry about that. But now, what does the negative in front of the function do to the function? And what it does is it reflects over the x-axis. Go in order. Read your equation left to right when you're doing these transformations. So we're going to do one at a time. So we're going to take our parent function here and so we're going to start with 0, 0. Remember, we're flipping over. So instead of one to the right and one up, we're going to go one to the right and one down. Instead of 2 spaces to the right and 4 up, we're going to go 2 spaces to the right and 4 down. And the nice part about these is that the other side is a mirror image. 1 space to the left and 1 down. 2 spaces to the left and 4 down. And do the best you can to make it not pointed because it isn't. There's our first transformation. Well, as we go along in the equation, we've got our parentheses and it says x plus 5 quantity squared. What does the plus 5 do to our function? How does it transform it? I'm going to go left. 5. So let's start with the vertex. We're going to move that left 5. Then we're going to take our point 1 and negative 1 and move it left 5. We're going to take our point 2, negative 4, and we're going to move it left 5. We're going to take our point 1, negative 1, negative 1, and move it left 5. And negative 2, negative 4, and move it left 5. So there's our second transformation. We have one more transformation occurring in this equation to our parent function. And that is coming from the minus 2. And the question is, well, how does the minus 2 affect it? Well, we're going to take our green graph now, and we're going to move all of those points down 2 spaces. Again, I'll start with the vertex. So moving that down 2 spaces. So the point 4, negative 1 moves down 2 spaces. The point negative 3, negative 4 moves down 2 spaces. Again, the other side is mirror image. With that point, negative 6, negative 1. I can't see it actually. Yeah, negative 6, negative 1 moves down 2 spaces. And negative 7, negative 4 moves down 2 spaces. And here we have our transformed picture. Problem number 2. We'll start like we do on all of the functions. Let's graph our parent function. Hopefully I can graph this one a little bit better than the last. 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. Those are our parent function points, typically. And once we have that graph, then we need to identify what's happening. And let's do it one by one. Read the graph left to right. And the first value in our graph is 1/2. And how does 1/2 transform our function? Well, it's a vertical compression by 1/2. In other words, what that means for us is we're going to multiply the y values of our points by 1/2. So for our vertex, 0, 0, 0 times 1/2 is still 0. Our next point is 1, 1. Well, the y value of 1 gets multiplied by 1/2. 1 times 1/2, so this is going to be 1, 1/2. Our next point in our parent function is 2, 4. Well, 4 times 1/2 is 2. So we're going to have a point of 2, 2 on here. And then we have mirror image on the other side. So we're going to have the point negative 1, 1/2. And we're going to have that point negative 2, 2. And I'm really sorry, again, the board is already disoriented. But again, we're going along, we're reading left to right, so what we see is inside the parentheses now we have negative x, and how does that negative inside the function transform our function? Well, this one reflects over the y-axis. Remember, with reflecting over the y-axis is sometimes you can't see that change, but we'll start with 0, 0. And then we're going to go one space to the right and 1/2 up, but we're going to reflect it over, so it's really going to be one space to the left and 1/2 up. And we would go 2 spaces to the right and 2 up. We're reading off of our red graph. 2 spaces to the right and 2 up is going to reflect over, and it lands over here to the left. But then what happens is all the left-hand points end up over here on the right side. And there is no difference, except that it's more oriented here on the green graph than it was on the red graph. So we have one more transformation. We've got a -4, which is outside of the function. -4 outside of the function means that we're going to finish by moving our green graph down 4 spaces. I like to start with the vertex, so we're going to move that down 4. And then we're going to move that point 1, 1/2 down 4. So now it's going to be 1 and negative 3.5. And move that point 2, 2 down 4, so it's going to be 2, negative 2. And then we have a mirror image on the other side. Negative 1, negative 3.5. And negative 2, negative 2. And there's the graph of our transformed y equals x squared. Again, if you have a graphing calculator, check it. Type it in. I know it says do not use, but why not check it so that you know that you have it correct when you turn in your quiz or your test in the near future. Number 3. F of x equals negative 2x squared plus 5. I'm going to start like we have been starting with graphing our parent function. Once again, it has the points 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. Looks roughly like that. But then we need to identify what's happening to the graph. And the first thing that's happening to the graph is that there's a negative in front of the function. And the negative is separate from the 2. How does that negative impact our graph? Well, it reflects it over the x-axis. So we're just going to turn that graph all upside down. 0, 0 is going to remain the same, and the vertex is going to remain the same. Then we're going to have 1, -1, and we're going to have 2, -4. We're going to have -1, -1, and -2, -4. When we flip that over the x-axis, by the way, here's x. That's the x-axis. This is the y. Like I said, the negative is separate from the 2, but the 2 is the next part in this equation that causes a transformation. And the 2 is the vertical stretch by 2. Vertical stretch means that our y values are going to get multiplied by 2. So 0, 0 is going to remain the same. But instead of going 1 space to the right and 1 down, that 1 down is going to be multiplied by 2. And we're going to go 2 down. 2 spaces to the right, that's not going to change. But the 4 down is going to change. That's the y value. The 4 down is the y value, -4. -4 times 2 is -8. Again, if you can get 1/2 of the graph, you can get the other because it's a mirror image. So we're going to have this point -1, -2. We're going to have this point -2, -8. When we vertically stretch our graph, we have one final transformation on this particular problem. We've got the +5. The +5 is outside of the function. And the +5, therefore, is going to move our graph up 5 spaces. So let's start with moving the vertex up 5 spaces. And then we're going to move that point 1, -2 up 5 spaces. So it's going to be 1, 3. We're going to move our point 2, -8 up 5 spaces. So it's going to be at 2, -3. And again, nice here when the graph is spread out a little bit more to do the mirror image here. We're going to have this point -1, 3. And we're also going to have this point -2, -3. And we've moved our graph up 5 spaces. And hopefully, again, that your picture is better than mine. One more here on the back of our notes, number 4, k of x. Well, let's start off by drawing our parent function, which is the 0, 0, the 1, 1, the 2, 4, the -1, 1, the -2, 4. Because that's the most basic of our functions. Then any transformation, we're going to use those values to help us with. We're going to start with farthest to the left in our equation, the 3. And we've kind of seen that before. This is going to be a vertical stretch. By the way, I'm only going to really be able to fit 3 points on the graph. I'm going to fudge it a little bit so that you can see the other 2 points. But really, I'm only going to be able to fit 3 on here. The vertex is still going to stay 0, 0. 0 times 3 is still 0. But now we're going to stretch. And in our parent function, we see that we went one space to the right and one up. That one up now is going to be multiplied by 3. 1 times 3 is 3. And like I said, I can't fit them all on because 2 to the right, that's not going to change. But 4 up comes from the parent function. And 4 times 3 is 12. So that's not going to fit on our graph. But like I said, I'm going to put a point up there. It's going to go off your graph if you're going to put that point there. And again, use this idea of mirror image. 1 space to the left, 3 up. 2 spaces to the left, 12 up. And there we vertically stretched our graph. Second transformation. -4 inside the function. Which direction do we move, right or left? And hopefully you're saying right. Because it's inside the function. We're going the opposite direction of what we think we're going to do. We're going to take this red graph and we're going to move it 4 right. Move the point 1, 3, 4 spaces to the right. Move the point 3, 3, 4 spaces to the right. And then our up 12s there, we can put up there if we so choose. I know only 3 points fit on this graph. Then there's one more transformation. +1. Well, +1 is going to move us up 1. I'm going to start with the vertex. So 4, 0 now becomes 4, 1. 5, 3 becomes 5, 4. 3, 3 becomes 3, 4 because we've got the mirror image. And now, instead of those points that are off the graph that go up to 12, they're going to go up to 13. Again, you decide whether you even want to put those on there. I know they don't fit on the graph. But there's our rough picture of those transformations there. Again, use your calculator to check your work. Why not? So on these last 3 questions here, we're given the graph of a parent quadratic function and a transformation of that function. And then we want to list the transformations that occurred and then write the equation of the transformed transformed function in vertex form. I'd like to take a slightly different approach on this. Our parent function has the origin as a vertex. As we take a closer look here, our transformed function, what's the turning point of that? And turning point, remember, also means vertex. Well, it's this point right here. And that is -3, -4. So I'd like to list the turning point. That's a personal preference there. But in fact, what happens when we find that turning point is we had to go left 3, and we went down 4. And we don't have any reflections on this graph. So the only other option is, do we have a vertical stretch or compress? But as we look at the vertex, we went 1 space to the right and 1 up. We don't have any vertical stretch or compression either. So if we write this in vertex form, this is going to be y equals. Remember, when we put something back in the parentheses, we change the sign. So -3 is here, so this is going to be x plus 3. And then we keep the sign. -4. There's our equation. Again, something you could type in the calculator. Does your equation match our transformed graph? That's given to us. If we look at number 6, same idea. The parent function has our vertex at 0, 0, a personal preference, what's the turning point of our new graph? And I'll put it in orange there. Well, our turning point of our new graph is 4, 3. And in fact, it's not the order that we put it back in the equation, but knowing that the turning point is 4, 3, what we did is we went right 4, and we went up 3, so there's 2 of our transformations. There could be more. In fact, what we see is that one of them, or that our new picture is turned over, it's upside down, and we call that a reflection. And it's a reflection over the x-axis. We only have one more other type of transformation that we do in Algebra 2, and it is a vertical stretch or compress. As we look at the vertex, we went 1 space to the right, but we went 2 down instead of 1 down. So that does mean that we have a vertical stretch. And again, we were thinking that we'd only go 1 space down because of the reflection, but we went 2 spaces down, so this is going to be a vertical stretch by 2. And now we have everything that we need to put it back into the equation. Y equals, first one that I'm listing is the reflection. Reflection is indicated by a negative. The second part of the equation is coming from the vertical stretch. We're stretching it by 2. And then we can do the rest. The parentheses change the sign. So it's going to be x minus 4. The sign is coming from the turning point, or the vertex. And then keep the sign. 3 plus 3. Finally, to finish. Same idea. Our parent function has the vertex at 0, 0, so we're looking at the other graph. In this particular case, there's our turning point. Turning point also known as the vertex, and it's -5, -2. And what that also tells us is that we went left 5, and we went down 2. We do not see an upside down parabola or quadratic, so we don't have a reflection. But do we have a vertical stretch or a vertical compression? And as we look, we start the vertex, we went 1 space to the right, but did we go 1 up? No, we only went a part way up. So we're going to have a vertical compression. And then as we take a look here, maybe we can tell from this first point, but we really can tell from the second point. We went 2 spaces to the right. Instead of 4 up, we only went 2 up. 2 is half of 4, so our vertical compression is by a factor of 1/2. And now we have everything that we need to write our equation. It's y equals, the vertical stretch or compress comes first, 1/2. Then our parentheses change the sign. So it's going to be x plus 5. And then to finish, keep the sign.